Now we know how to represent the voltages and currents as a function of Fourier series. And we know how to calculate the average power or real power from the Fourier series functions of the voltages and currents. Now in this case, let's say you're talking about a pure sinusoidal voltage and pure sinusoidal current. That means you're talking about the fundamental voltage and fundamental current. Let us assume that. In that case, you can say that we're talking about not having any DC. So that means your V0 DC and I0 DC are 0. So that means this term is 0 for us. And then we have only sinusoidals of the voltage and current that corresponds to fundamental, that is n equal to 1. So, and there are no other harmonics. So in that case, the RMS value of your voltage is going to be V1 RMS. RMS value of your current is going to be I1 RMS. And there will be a phase angle difference which will be pi 1 minus phi 1. So theta 1 minus phi 1. Now if we want to get the power factor of this particular power, it is power, that is P, real power, divided by MVA or S. The way we express S is an RMS value of voltage and current. And now, the total RMS need not to be always same as the fundamental RMS value of the voltage and current. That is where the power factor comes into picture. But in this particular case, where we consider that there are no DC voltage and current components, and there are no harmonics voltage and current components, then the average power that we have is nothing but V1 RMS and I1 RMS cos of that phase angle difference. And the S is nothing but VRMS and IRMS. Both will be exactly same as the fundamentals because we don't have DC, we don't have harmonics. So this RMS values, the total voltage RMS and total current RMS, will cancel out with the first order or the fundamental voltage and current terms. Then we'll have power factor as theta 1 minus phi 1. But there could be a case where your voltage is a pure sinusoidal, you are supplying a pure sinusoidal voltage, but you are getting a current which has harmonic components. And where will be that case? Let us say you have a rectifier. So that's what we were talking about it in the beginning. So if you have a rectifier which is expected to convert your AC into DC, your source could be a sinusoidal voltage. So your voltage is sinusoidal, but your current is not going to be sinusoidal. Your current is going to be pulsating, whereas your output current I0 is going to be constant. So in the rectification process, you're getting a direct current from a sinusoidal source of the voltage where your source current is having harmonics. This is the case where you have your source voltage as a sinusoidal, your source voltage is sinusoidal, whereas
This is a message from Ames Community School District. The Ames Community School District is delaying start times by 2 hours on Tuesday, February 18, 2025, due to extreme cold weather.
So this is the conversion process where we have source voltage as a pure sinusoidal, but our source current is having harmonics. Suppose if we have a case where our source voltage is pure sinusoidal and source current is having harmonics, not just a pure sinusoidal, that is when you can see that your VRMS and IRMS is going to be different from your I1 RMS. So that difference will make your power factor to be not just cos theta 1 minus phi 1. Now we thought of a case where your source is going to be a pure sinusoidal voltage, but your source current need not to be a sinusoidal current. It can have harmonics and it will be represented as a Fourier function. Now in that case, how will be your power factor different from the way we have seen the power factor? Now, if you look at the RMS values of the voltage, yes, that V voltage RMS is going to be same as the fundamental RMS. But the current RMS is going to be different from the fundamental current RMS. So if you look at the power calculations, we know that the average power, that is power average, is the real power value that is corresponding to only the voltage and current which exist. Now we don't have the real power or an average power that corresponds to DC. We don't have the average power or real power that corresponds to higher frequencies. So the real power that is only corresponding to fundamental voltage and fundamental current and the respective power factor. The reason is we don't have the source that is supporting the real power or an average power of the higher order frequencies. If you look back and see, the value of the power or a real power value is depending on the voltage and current that corresponds to DC if you have, and voltage and current RMS values which does exist of the same frequency. Now we know of a case where the source voltage can be purely sinusoidal, but the source current can be a Fourier series function. Source current does have higher order harmonics and it is a pulsating DC. Now in that case, how will be your power factor? How do we calculate that? Now let us consider that you have a source where voltage is a pure sinusoidal, and then you have a source current is non-sinusoidal and it is expressed in terms of a Fourier series. For this case, if you try to calculate the value of the real power, in this case the real power is going to be only corresponds to the fundamental value of the voltage and fundamental value of the current. That is, voltage corresponds to omega naught and current corresponds to omega naught, because since we don't have any voltage that corresponds to the higher frequencies, then the real power or an average power doesn't exist for that frequencies. So if you look at the power factor, average power by MVA power or SCA, S value, if you look at the power factor, which is average power divided by S, the average power is only corresponds to the fundamental value of the voltage and fundamental value of the current and the corresponding power factor. But if you look at the VRMS and IRMS, IRMS is not just I1 RMS, it will also have a different currents, because my current is a function of a DC current and higher order functions. So that is going to be different for me. But voltage V1 RMS is exactly same as VRMS because my voltage doesn't have any higher order terms. So the voltages will get cancelled, currents do exist, which tells you that the power factor is not just same as cos theta 1 minus phi 1, it is also multiplied by I1 RMS divided by IRMS. In the previous case where your IRMS is just equal to I1 RMS, you do not have any harmonics, then the power factor is same as cos theta 1 minus phi 1. But now it's not. Means there is a deviation from the actual power factor. In a way, you also know that yes, my power is not just this P average, I am having something different, because my current is there or a current is present which corresponds to different frequencies. So that is actually telling that there is a distortion of your power factor. In a way, we say that if you wanted real power and reactive power in general, then you wanted real power and reactive power. The apparent power that you get S is supposed to be the sum of real power and reactive power here. This kilowatt and kVAR, but apart from these two, we have deviated by a factor, and the factor by which you have deviated and drawing an excess current is basically this distortion factor. In conclusion, what do we like to say here is that yes, when you have a source supplying a sinusoidal voltage, but you're drawing a non-sinusoidal current, then you are actually having some distorted value of power which you really don't want. It is neither real power or reactive power. It is nothing but the distorted power. That's how we consider, and the factor by which this power is distorted from the fundamental power is I1 RMS by IRMS. So whereas this is what is the power factor of the system when you are drawing non-sinusoidal currents from a sinusoidal source. if you want to solve a problem, let us assume that I have a source voltage which results in a non-sinusoidal source current. So the voltage and current expressions are given here. Now how do we get the value of the power factor and value of the distortion factor? In order to get the value of the power factor and distortion factor, now you know that the average real power does exist only for omega naught of the current and voltage, that voltage and current that corresponds to omega naught. You don't have any average power that corresponds to the DC current as well as the second harmonic current. Now, if this is the case, then you need to get the distortion factor, which depends on, you can see that the expression for the distortion factor, that I1 RMS by I RMS. And you can get the power factor as the cos of the phase angle difference between the voltage and current. Now, that power factor we can calculate first. Let's get the value of I1 RMS and I RMS. I1 RMS is I1, you know that the fundamental frequency related current 2.65 cos omega naught t minus 73.5 degrees. RMS value of that is 2.65 by root 2. You got I1 RMS. Now, RMS value of the total current is nothing but square root of I0 RMS square plus I1 RMS square plus I2 RMS square. Now you have the total RMS current. Now after you have these two, and also you have cos of the phase angle difference between the voltage and current that corresponds to the fundamental frequency, that is minus 25 minus of minus plus 73.5. If you substitute all of that, your power factor is supposed to be cos of the phase angle difference between these two multiplied by the I1 RMS by I RMS, and you will be able to get what is your resultant power factor. If you want to know what is just the distortion factor, it is the ratio between the two currents, that is 0.5793 that we have in the previous expression.